and welcome to the webinar, Challenges and Solutions of Electrode Mixing, with our guest speaker, Jillian Graves with IKA. Hi, Jillian. My name is Myra, and I'm the Director of Member Success at Volta Foundation. Just want to thank everyone for joining in today. We've got a great audience. Jillian and the IKA team have put together an incredible program for today, but before we get started, I just wanted to share a couple of tips and tricks with the webinar platform to make the program more effective for everyone. So if you take a look, so everyone in the audience, if you take a look at the right-hand corner, you'll see three different sections. I think, Jillian, you might have a little visual for this. First is an icon with a question mark. And the second is an icon that looks like a little report with a paper clip. And the third is a gear icon. So the first icon with the question mark, this is to ask questions during the program. So you can click on this, ask any questions throughout the program, and Jillian will come back on after her presentation and answer as many questions as possible. So if you click on the second icon with the little paper clip, you'll see there are three different handouts. There's today's slides, which are amazing. Thank you, Jillian and IKA, for sharing those today. And then two additional informational brochures about IKA and the content shared today. And lastly is the little gear icon. So if you click on this, there's troubleshooting for audio, or any kind of troubleshooting for the platform. But if you do have questions, you can always reach out to us at ms@Volta Foundation, and someone on the team will help you out. Okay, so that's the platform introduction. Before we introduce Jillian, we wanted to check in with everyone today. We have a quick poll to get us started. And we're curious to know, how much do you know about electrode mixing? So let's take a few seconds. I'll kick off the poll. All right, Jillian, you ready?
We're ready.
Get started. All right. All right. We want to know, who are the experts in the room? Who's here with a little bit of knowledge, and who's here starting?
Nice. We've got some godlike knowledge.
Oh, look at this. I love it. All right. So it looks like majority of the audience, Jillian, will be, knows a little bit.
Yeah. Perfect.
I like the why am I here? That's great. Okay.
You're very honest. Yeah, we love to see it.
Okay. I'll end it now.
Great.
And if anybody's curious, here's what we have. Here's the mix in the room today. Okay. Now let's get to know Jillian. Jillian Graves is a systems engineer in the battery division at IKA. She brings valuable experience in lithium-ion dry electrode process development, acquired through her previous roles at Tesla and the EPA. She holds a degree in chemical and biomolecular engineering from the University of California, Berkeley. And Jillian has made significant contributions to Go Bears. Has made significant contributions to advancements in dry electrode mixing, battery electrode calendaring, and powder metrology. Presently, she dedicates her time to collaborating with battery manufacturers, ranging from pilot scale to gigafactories, to devise electrode mixing processes that excel in both product quality and production efficiency. And Jillian is passionate about sustainability and the ever-evolving fields of technology and energy innovation. And it is evolving quickly right now. So we're thrilled to have you here today, Jillian. Thank you so much,
Myra.
And I'll hand it over to you to start today's program.
Perfect. Yeah, thank you so much, Myra, and thank you to the Volta Foundation for hosting this webinar. And thank you to our lovely audience members. I hope for everybody from godlike knowledge to why am I here, that we'll all learn a little bit and have a good time and listen to some horrible puns and pop culture references. That's what we're all about. I am going to turn my camera off for a little bit just so I'm not distracting from the content or slowing down the video, but I'm still here. Okay, awesome. So why are we here today? We're here to talk about the challenges and solutions of electrode mixing. And you might ask yourself, why does that matter? Why is that important? And I ask myself often, why did I spend the last 4 years of my life working in this field? Well, the answer, if we dig into what a battery cell actually is, becomes quite evident. So the electrode, for those of you that may not know, is the portion of the battery that is going to facilitate the ion transfer of lithium ions and electrons, depending on your state of charge. So whether you're cathode and you're gaining the lithium ions, or your anode and you're gaining electrons, it's a very crucial part of the battery. So being that that is true, having a structure of your electrode that is homogeneous and mechanically strong is very, very important to the overall performance of your cell that goes into everything from battery cells to cell phones. It's a very important part. We can see, as illustrated by the graph on the right, that there is also a strong financial incentive to learn about battery manufacturing and particularly electrode mixing. We see that the projected growth of the global EV battery market is projected to hit $400 billion by 2025. So we have explosive growth, and we have the desire to produce non-explosive cells, right? We've all seen the headlines. We want to produce batteries that are durable, efficient, and safe. So let's go through a little bit of the agenda today so you guys can know what to expect. Firstly, we're going to tackle the challenge of solid incorporation times. Why are they important, and what tools, what first principle tools can we use to effectively reduce this time? As Myra mentioned, the field of batteries is rapidly expanding and innovating. So we're going to talk about some new technologies and how we handle those technologies based on their application. So different pieces of equipment and different processing that we can use for these new technologies. We'll then give you guys an idea of what it looks like to transition from a lab to a mass production scale. And we will look a little bit at some heuristics to optimize that portion, which can be a quite costly portion, so very important to understand. And then we'll take a little break from electrode mixing so I don't put myself and all of you guys to sleep. And we'll look at a conical dryer case study. I find this to be a really interesting piece of equipment, uses lots of first principle engineering involved. So I think that will be quite fun, also related to lithium precursor production. And then, of course, I'm here with IKA today. So I would love to talk to you guys about some of IKA's core competencies and why I think they're awesome. And then we will round out the hour with some Q&A from you guys. All right, great. So I want to keep everybody involved. So we're going to go ahead and kick it off nice and strong here with another poll question. If Myra would be so kind as to queue it up. We want to know from you guys, what is the average energy density, and we're talking about a mass density here, of a lithium ion battery cell? Great. See the answers coming in. Okay, great. No one's taking the bait on the the ridiculous units that we put. Yeah, this looks really good. Okay, perfect. It looks like the poll has ended, and you guys are experts in the field. 91% guessed 150 watt hours per kilogram, which is right in the ballpark that we expect for a typical lithium ion battery cell. Of course, we have a range. It can range from around 100 to 200, but for the sake of an average, the 150 watt hours per kilogram is correct there. Myra, do you want to share the results of the poll? I just want everyone to see how awesome they did.
Yeah.
So,
I'm
uh,
sharing now. I'm not sure if you can see it, but
yep,
yeah,
yep.
it looks like 91%. All right.
All right, cool. I got a thumbs up. Okay, great. Oh, thank you. Okay, great. Everyone can see. Yeah, you guys are brilliant. All right. Um, so keep that in mind. Keep that number in mind because we are going to use it in just a little bit as we talk about reducing our solids incorporation times. So as you see on the image on the left, my coworker found this really cool image that I like because it shows how the homogeneity of your final product is very affected by your mixing technique. We see the food processor and the blender do a much better job of homogenizing your mixture versus looking at the spoons that contain the mixture mixed with the whisk and the sieve. So let's talk about what drives that. Or if you're Neo from the Matrix, you might just say, there is no spoon. So, getting into a bit of a case study here, why does solid incorporation times matter? Can't we just throw everything in the mixer, mix it for as long as it's going to take, 12 hours, what have you, and call it a day? Sounds great, right? Well, at the pilot scale, yes, you might be able to do that. But we start to see this being a challenge when we want to scale up to the giga scale. So let's do just a few back of the envelope calculations to figure out if you have a factory and you want to produce 1 gigawatt worth of batteries in 1 year using an NMC battery chemistry. How much electrode will you need to produce? And what cycle time will you need to be able to hit that mass quota? So we start by using our previous knowledge about the average lithium ion cell density, and we're going to multiply that by the 1 gigawatt of energy that we need for our gigafactory to get our total mass of the active material that we will need for our factory. So we see that we're going to need around 6.7 million kgs of active material to be able to reach that energy. Now we need to look at how much of that is actually coming from the cathode and how much of that is actually coming from the anode. Now this is going to vary depending on your N to P ratio. However, for the sake of this exercise, we're going to assume that we need 52% of cathode by mass and 48% of anode by mass. A relatively safe assumption. Usually you need a little bit more of the cathode by mass, it tends to be heavier. So if we take this 6.7 million kgs, multiply it by the respective percentages, we see that we're going to need around 3.5 million kgs of cathode material and 3.2 million kgs of anode material. All right, great. So how many batches does that translate to? For the sake of this thought experiment, we're going to assume we have 1,000 kilo batches. This is quite a safe estimate. If you want to go higher, you may have challenges with your thermal mass, and going lower, we may need more and more batches, right? So this quick calculation, 3,500 cathode batches and 3,200 anode batches that we need to mix in the year to hit our target. Now we need to look at the available runtime of the tool. As those of you who are in manufacturing well know, just because you have the tool year-round does not mean it will run year-round. We have to take time for maintenance. We have to take time for unplanned downtime. So for the sake of this thought experiment, we assumed an available runtime of 80% of the year. So if we are actually mixing for 80% of the year when our equipment is up and running, and we divide that by the number of batches, we can see here that we need a cycle time of our cathode of roughly 2 hours and a cycle time for our anode of roughly 2.2 hours. And I'm happy to provide sources for all of these references, of course, if requested. So why is this a problem? Well, if we have 2-hour mixing cycle times that we need, we either have to meet that quite stringent mixing time, or we need to add more mixers. And more mixers are going to require more floor space, more capital initially to purchase the mixers, and then of course, more OpEx. You need operators to run the mixers, you need engineers to oversee all of that. So your process quickly becomes complicated, adding these additional mixers. So how can we avoid that? How can we minimize the amount of mixers that we need and at the same time produce the amount of electrode material for our target? Well, the answer to that is going to lie in our cycle time and keeping our cycle time down. So the challenge with the conventional electrode mixing that the industry is facing right now, if you take a look at the graph, we can see energy consumption on the y-axis and time on the x-axis. These are averages taken across the board. If we assume we have a batch volume of 400 liters and assuming an average motor power of 15 kilowatts, this is what a typical life cycle of an electrode mix looks like. So we initially start with feeding our solids. These are going to be materials such as our active materials, our LFP, NMC, graphite, as well as some potential conductive materials or additives. We are not counting any energy expended here because we're going to assume that we are feeding these solids to a stationary mixer, but we are assuming a pretty liberal estimate of roughly 10 minutes to feed your solids. The next step is going to involve feeding your liquids. These will be your solvents or any liquid additives. This could be NMP, water, acetone, all of that kind of liquids. We're going to assume that the mixer is turning for this portion, and we're going to budget around 45 minutes on average for feeding these initial liquids into your mix. So then typically we have the next 3 hours which are spent on mixing and solving the solids completely into the mixture. And during this process, we are depending on the bulk turnover to reduce agglomerates and get a homogeneous mix to the specification that we need, reducing the particle size to the specification that is also needed, and hitting that target viscosity. These are all measurements that can be conducive to telling you how well mixed your mixture is. And then most mixers will need to be cleaned between each batch. Not all of them, but definitely we need to budget some time for discharging the mixer. And we assume that the mixer is off for this portion. So we see by the end of this that our cycle time is currently around 4 to 5 hours on average, and we're currently expending about 60 kilowatts of energy during this process. But we just mentioned that for a gigafactory, we need a 2 to 2.5 hour cycle time. So therein lies the challenge. And this means we're going to need more mixers, more capital, and more operating expenditure. We have this little graphic of the solids being dissolved. And Studio Ghibli actually touched on carbon agglomerates as well in Spirited Away. We have these cute little carbon agglomerates, but we don't want them in this case. We want to solve them completely into the mixture. And I just think they're very cute, so I wanted to put them in. All right, wonderful. So, how can we improve our bulk mixing? Um, as my fellow chemical engineers know, Perry's Chemical Engineering Handbook is the Bible. So we look to Perry's Chemical Engineering for some mixing heuristics that we can follow to make sure that we're optimizing our mixer for ideal bulk mixing. One of the first things you're going to want to do is measure your fluid viscosity and determine your density so that you can calculate your Reynolds number. Knowing whether or not you are in a laminar or a turbulent regime additionally will help you when making these assumptions and sizing your mixer correctly. So if we look over here at this image of the tank, we have a couple dimensional parameters. We have Z equal to the height of the liquid in your tank. We have parameter D, which is equal to your impeller diameter. We have the total tank diameter, and we have the distance from the bottom of the impeller to the bottom of the tank, which we will call C. So we see from our first heuristic that the impeller diameter should be roughly 10 to 20% of your total tank diameter if you're dealing with a low viscosity fluid. So this is going to be the ideal dimensional parameters for low viscosity. If you have a high viscosity fluid, you need more agitation to move that bulk material, and you're going to shoot for your impeller diameter to be roughly 35 to 50% of your total tank diameter for that. Next, we look at the ratio from the bottom of your impeller to the bottom of the tank over your entire tank diameter. So this parameter C should be roughly 10 to 40% of your total tank diameter for you to be in an ideal bulk mixing range. And then we look at the liquid level Z. The normal range for your liquid level should be anywhere from 20 to 120% of your total tank diameter. If you are exceeding that liquid level range, you should definitely consider adding impellers to your agitator to improve your bulk mixing. So following these heuristics, we can already improve the bulk mixing in our tank. However, I did want to call out something of importance from Perry's Chemical Engineering Handbook, which tells us that the energy dissipation per unit volume around the impeller is approximately 100 times higher than the rest of the tank. This is quite intuitive to think about. Of course, your area surrounding the impeller will have that higher energy dissipation, which is what will ultimately lead to your agglomerates being completely solved in your liquid. So with that in mind, we want to increase that energy dissipation per unit volume. So we have kind of two levers that we can play with. We can either make a larger impeller, or we can reduce the volume surrounding that impeller to be able to take advantage of this increased energy dissipation. So as a quick thought experiment, what is the probability that an agglomerate will contact this high energy dissipation region in your mixer? Well, if we look at the mixer on the left, an agitated vessel type mixer, we have a total volume of 500 liters If we assume an impeller diameter of just about 1 meter, that impeller is going to sweep roughly 5% of the total area of your tank, which means 5% of your material will be in that high energy dissipation regime. This type of mixing is very dependent on bulk turnover, which will again depend on your fluid viscosity and your fluid properties. Something that IKA does really well is that we take advantage of this heuristic by reducing that volume in which your solids and liquids are meeting. So you still have the same amount of mass flow going in, you still have your 500 liters, but it is an inline flow rather than a batch mix. And you're combining your solids and liquids in a small chamber with a large impeller, where your impeller is actually going to sweep through about 90% of this area as opposed to 5% of the agitated vessel. So 90% of your solids and liquids are entering in that high energy dissipation regime that we just talked about. So this is one creative way that you can take advantage of that property and get your mixing time down. It can be a little tricky to see what's going on in the machine on the right. So I'm going to zoom in really quick to give us a better view. So in that small chamber, my mechanical engineering friends will know well what rotors and stators are. Basically, we have these light blue, let me get my laser pointer, light blue rotors. These are rotating around in a circular motion. And we have these dark blue stators, which are stationary. We have our solid and liquid particles coming in from the center, these large yellow agglomerates. These agglomerates now must pass through two rotating rotors and two stationary stators before coming out on the other side, and the agglomerates are solved using this dispersion technology. All right, fantastic. Now that we've talked about a few of the heuristics to help you optimize your mixing parameters and reduce your solid incorporation times into the mix, we are going to talk about what I like to call the final frontier of battery manufacturing. Um, Obviously not the true final frontier, but for where we are right now, there are some really exciting new technologies on the scene. We have, of course, dry battery electrode, something near and dear to me, which has so many advantages. We have a much higher energy density and a faster charge time. That comes from not having to evaporate your solvent off and leave any interstitials or void spaces in your electrode. You're instead making use of the entire volume as electrode material. And then, of course, from an environmental standpoint, you're not using that solvent, so you're not using any NMP or generating any wastewater. And additionally, you don't have the energy expenditure from large ovens that might need to be used to evaporate that solvent. So very interesting technology, very promising, but of course some challenges to handle there. And then in the center here, we have innovations in material science, which I will not pretend to completely understand, but from a ramifications point of view and from a processing standpoint, these high energy density chemistries can require some special handling that we'll talk about. And of course, more and more in the industry, we are seeing the integration of these superconductive materials. So these carbon nanotubes, these graphene-like structures, which can greatly improve your charge times and increase your energy storage. These can also prevent the dendrite formation on your lithium metal anodes, so very important there. And of course, they have exceptional mechanical strength. Sorry, just 1 second. Can you guys still see what I'm sharing? No. Okay. Oh,
I can see
okay.
it. I can see it. Yep.
Yep, it's back. Okay,
Looks good.
cool. Thank you.
Hmm.
Um, Anyways, great. So moving on. Yes, we have our superconductive materials. So let's talk about each of these new technologies, some of the challenges associated with them, and some resources to go ahead and solve some of these challenges. So the first thing we'll talk about is dry electrode. It's a relatively new process when we compare it to our wet slurries. And of course, one of the main challenges here is that your material is dry. And as we all know, dry materials do not flow in the same way that we would expect a liquid to flow. As we've all learned this year, these past few years, the spice must flow. So properly sizing our hoppers becomes of the utmost importance. So we can see here on the leftmost hopper, we are seeing an effect which is known as rat holing, where you have an unidealized hopper half angle, where you're actually flowing down the funnel. You're not getting first in, first out of your hopper, and you're not going to get the best quality of material coming out of this hopper. We then see this middle hopper showing us an example of a bridging concern. This can again happen from an incorrectly sized hopper, not taking into account your specific powder properties, where you can actually form a bridge at your outlet and not get any flow out of this hopper, even though you would look at it and think that it is full. Extremely frustrating, extremely costly to production, and extremely annoying to have to vacuum out. Um, and then the final hopper, we see the good hopper. This hopper is experiencing a phenomenon called mass flow, where we are seeing a first in, first out process of material flow out of our hopper. Some great resources for properly sizing your powder hoppers is going to be this textbook, Storage and Flow of Bulk Solids. It's kind of one of my Bibles that I have on my desk at all times. Goes through how you can properly size your hoppers using just a rheometer and measuring some of your powder properties so that you don't experience these frustrating challenges. Another challenge with our dry electrode material is the actual depositing of the dry material onto your metal electrode. So this process can be called calendaring, can be called lamination, whatever you call it. This is the actual process of depositing your solid material onto that metal. The most important thing here is that you are aware of the method in which your material is flowing onto that material. And some resources that I can recommend for that would be looking into Jenneke and Johansson, discrete element modeling. That will be quite helpful, where you can use the specific properties of your material to look element by element at how that flow and how that process will take place. And with dry electrode, being that it is a relatively new technology, it's very, very important to have a mixing machine that is versatile. Right, with any new technology, we're going to have changes to formulations, we're going to have changes to processing conditions that we need to meet. A mixer that I really like right now is this IKA HKC machine. This machine has anywhere from 6 to a customizable amount of chambers where you can actually control at each individual mixing chamber the temperature, the speed, the pressure, and you can also control where you're introducing your solids into the process. But whichever mixing machine you are choosing, make sure that it's one that is versatile with ideally as much temperature, pressure, speed control as possible to be able to accommodate for the changing landscape there. But yes, very exciting technology, definitely. Now, if we touch a little bit on the high energy density chemistries that I mentioned, as I mentioned, I am no material science, but I am an engineer that has to deal with these materials quite frequently. And the biggest thing that I've noticed here is that you need an intact crystalline structure. These high energy density chemistries are oftentimes very dependent on not breaking the structure that is going to store your ions. Um, so there's a few things. Some of them are unavoidable and some of them are avoidable that can cause damage to this material, such as oxidation, cell cycling, so your actual charge and discharge of your cell, electrolyte exposure, again, somewhat unavoidable, can all damage material, as well as particle to particle collision. So for the oxidation, cycling, and electrolyte exposure, there are some surface coatings that you can apply to your active material that will actually reduce these side effects between your oxides and your atmosphere or your electrolyte. And I'm happy to chat about that offline as well. And then for your particle to particle bombardment, when you're mixing these types of chemistries, you're going to want to choose a gentle mixing tool. So I'm just, for the sake of it, showing the IKA mixing options. For the disperser, you can see on the left, these mixing tool 0 and generator P have very large gaps for the particles to flow through. So we are not imparting a ton amount of shear energy here. And as we move to the right, we see more and more shear energy being imparted as these gaps get smaller and smaller, forcing the particles to move through there. So if you have a breakable material, yeah, make sure you're choosing a gentle mixing option there. And then the other end of the spectrum, yeah, let's talk about if you have a really robust material. For example, some of the advantage of these carbon nanotubes is their mechanical strength, and that's wonderful. When you have a really robust material, I would highly consider potentially moving away from a batch process altogether and looking towards continuous mixing. Um, the advantages from continuous mixing are fairly obvious. You do all of your process steps in parallel. You're feeding liquid, feeding solid, mixing, and discharging is happening simultaneously. Um, and this leads to a decreased energy consumption by about 7-fold and a decreased cycle time, again, as low as 1 hour. Um, so you can use this continuous mixer in conjunction with a batch mixer. I don't think it's a bad idea to have the continuous option if you have additives or something that maybe you want to add later on down the line. You can have this continuous option and do some of your mixing in a batch option as well. So with this, you'll see a decrease in your cap and OpEx and more efficiencies here. So about 6 kilowatt hours of energy in about a 1 hour cycle time to process the same amount of material as in a batch form. So robust materials are great when you have them. Awesome. All right. So now, if we talk a little bit about what the life cycle to transition from lab to pilot to mass production looks like. Um, yeah, the bad news is it can take, on average, 7 years or more for companies to be able to achieve stable production at scale. And that is largely because you have about 600 different process characteristics your machine set points, your equipment, your specific recipes that go into the production of these lithium ion batteries. So your multivariable problem quickly expands and blows up. So if we look at this graph in the center here, we can go through what that typical life cycle might look like. So we start over here, the first 1 to 2 years with our proof of concept. This is usually going to start with some modest investments or self-funded, around $100,000, $200,000 to get to your prototype production. At this stage, around years 2 to 4, during your prototype production, you will aim to optimize your process and keep your costs as low as possible. Once your prototypes have been proven out and you are hopefully getting more funding at that point, you can go into your low volume production or pilot production. This is typically in place around year 4, and your low volume production can begin. The amount of materials you produce will still be in a very small amount, and you'll still be doing lots of R&D close to the production line. Years 4 through 7, we typically see are spent in the growth phase of that low volume production, growing that to a mass production scale. Process parameters are going to play a key role here in this scaling. And then eventually at around 10 years, on average, you can expect to be in the mass production stage. By this point, you may have expended on the order of hundreds of millions of dollars, but then your spending will decrease when you enter the mass production phase. So how do we make the scaling as easy as possible? There's a few heuristics we can follow for scaling the mixing process. There's typically 2 methods that you can use for this scaling. One is you can build a model based on your pilot plant studies to better understand your process variables. The pros and cons of that is that building a model requires quite a bit of time and effort up front. And even the best model is still not foolproof. And every time you make a process change, you will need to revisit and redo your model. The other way to go about this is to just run experiments rather than focusing on modeling building. Focus on collecting empirical evidence by running these experiments on the large and small scale to better understand the process. The con here is that this can be quite expensive to run these experiments on that large scale. But if we follow some general heuristics, we can see that the Reynolds number, the blending times, and your heat transfer that you need to demand in your tank will all increase as you scale up. Now, if we dig into those process parameters and which process parameter is most important, depending on your mixing scale, when you're mixing in the macro scale regime, which we define as particles above 100 microns, the most important parameters that are going to influence your mixing here will be your geometric design of your mixer, your power, your impeller speed, your impeller diameter, and your blade shape and dimensions. However, when we look at the micro scale of mixing, if we're mixing particles at the 100 micron scale or less, the important variables there become your power per unit volume, your root mean square velocity, your energy spectrum, your dissipation length, and your viscosity of your fluid. So depending on which type of mixing you're trying to optimize, you would look at these variables for that. Excellent. And yeah, just a brief segue about how we do the scaling here at IKA. One of the cool things about IKA is that we have the same type of equipment available from a lab scale to the pilot scale, to the mass production, and even offering the complete turnkey solutions with your bulk bag unloaders, pumps, tanks, all that, so that at least you are using the same machine from the small scale to the big scale. We also utilize integrated modeling that we have to bring our R&D to full-scale production. You have the benefit of dealing with a single vendor, and we also have pilot testing centers available for your use all over the world. So we can actually make the trials with these small machines and then use our modeling to go ahead and scale that up to the mass production machines. So very important to select your equipment wisely when you know that you're going to be scaling, and make sure that there is a plan in place for that scaling. Okay, great. So Myra's going to queue up another poll for us, and we're going to ask, does water take longer to boil at higher elevations? True or false? Interesting. Awesome. Yeah, seeing the votes come in. Great. Still got some folks awake out there. Love to see it. Okay, great. So we have 39% of the audience selected true. This is a bit of a tricky question, and 61% of the audience selected false. So if we take a look at our phase diagram, when we are at a higher elevation, we take this normal boiling point and we decrease our pressure. So if we follow along this liquid vapor equilibrium line, we see as our pressure decreases, our boiling temperature will also decrease. So water will take less time to boil off at higher elevations. However, as my colleague Stuart pointed out, this is kind of a tricky question because cooking will take longer at higher elevations. Because your temperature is lower, you will actually need to cook for longer. So that might be why some folks got confused there. But your water will actually boil at a lower temperature and faster at a higher elevation. So why is this important? Because we're getting into our case study about lithium dehydration. So this is a really cool process that is required for precursor production. What we see at the first part of this process is that we have lithium brine, which is pumped from deposits or salt mines. A lot of these are in South America. And then we have this brine being concentrated via evaporation, and we can then process that into lithium sulfate or lithium chloride. After a series of crystallizations and separations, lithium carbonate can be treated to create lithium hydroxide and lithium hydroxide monohydrate, which is just a lithium hydroxide with a chemically bound water molecule attached. And then that compound can be further dried to produce our battery grade lithium hydroxide monohydrate. So for our case study, we're going to focus our attention surrounding this process right here, where we're going to look at drying the lithium hydroxide monohydrate, and we're going to use a requirements of 0.5% residual moisture. We want to keep our drying temperature below 150 degrees C to not damage anything, and keep our lithium carbonate below 0.01%. So in this case, we looked at our conical dryer. That's this piece of machinery right here. The benefits to this piece of equipment is that it actually uses vacuum to lower the boiling point of your water and faster evaporate it off. So this machine is imparting heat energy through the walls as well as through the central spiral agitator, and then again, dropping the pressure using the vacuum. So we started with 100 liters, 100 kgs of material, temperature around 80 and pressure around 250. So as we see on the graph on the left, when we first started out, even though we were imparting heat energy, the heat of our material was not rising until we got to about hour 4. And we know why this is. This is because the heat that we are imparting is going towards evaporating the water instead of the specific heat of the material. So we look at this data and we assume that right around hour 4 is when most of our water has evaporated because we are actually seeing a temperature increase in the bulk material at that point. This is concurred with the graph on the right where we look at the pressure. Even though we are applying a vacuum, the pressure is not really dropping until we get to about hour 4 again. And this is because we are generating pressure from the moisture being evaporated. So once we see these two characteristics in terms of the temperature increasing and the pressure dropping, we can assume that we have evaporated most of our moisture at that point, perhaps not chemically bound moisture, but most of our surface moisture. And this was corroborated by our final test results from sampling the material around half an hour in. We had about a 35% by mass moisture, and right around hour 4, we actually exceeded the customer requirement with 0.15 mass percent of moisture remaining when our criteria was 0.5. So this is just kind of a cool case study showing that you can take advantage of first principles engineering, take advantage of our VLE diagrams to be able to impart less energy and save time and achieve the same result. So this is a bit of an example of what we would do at IKA and how we work with clients to meet their criteria. And this was a trial that we did perform. Fantastic. A brief word about our IKA solutions. So we talked a little bit about this batch mixing machine right here for electrode mixing. We talked briefly about this material dryer as we just went through with the case study. While talking about dry electrode, I briefly showed this continuous kneading machine where you can control each chamber temperature, pressure, and speed. And then on the right here, we're showing what a typical IKA turnkey solution might look like from your raw material bulk bags coming in, your degassing, your mixing unit, and your final deagglomeration before sending downstream. All right, fantastic. And just about the top of the hour, your mix is ready. And we're ready for some questions now.